Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 20 and we will be looking into carrier freeze out and its related effect in semiconductors. Now if you look at the Fermi energy and the Fermi Dirac potential, then we know that the probability function of an electron is given by this quantity, right? And it is quite interesting that if your donor, so ED is the donor level and EF is the Fermi level. If the difference between ED and EF is large, right, if this difference is large, then the denominator actually becomes large, right, and therefore this falls down. It effectively means that if the donor level and Fermi level are very far apart from each other, I would actually expect to see the number of free electrons available donor will be relatively small, and that is where the whole sort of freeze out concept comes into picture, or even incomplete ionization. Now if I say that the donor level is fixed, but EF happens to be a function of temperature, then if I increasing or decreasing the temperature, EF becomes closer to ED, then my ND, small ND will go on increasing and you will have a larger probability of finding electron. Whereas it is the other way around, if I reduce the temperature and the Fermi level becomes much further away from the donor impurity, then this terms becomes excessively large, right, and therefore this will go to 0, and that is basically known as freeze out, carrier freeze out. There are no free charge carriers available to you at certain temperature. If we assume that ED minus EF is greater than KT, so I can take this much larger as compared to 1 has been removed, and from here I get 2 ND exponential minus ED minus EF by KT. That is the value of ND which you get, and that is very straightforward to look into. Now if ED minus EF is this quantity, is much larger as compared to KT. KT is again an energy term, right? Then the Boltzmann equation is also valid for electron in the conduction band EC minus EF. So my donor species basically comes very close to the conduction band edge, and therefore I can write down N0 to be equals to NC exponential EC minus EF divided by KT, right. EC minus EF is the conduction band edge minus the Fermi level edge, right, that becomes with the negative sign, of course, right. Now we need to find out the ratio of the electron in the donor state to the total number of electrons in the conduction band plus donor. So there are two elements. One is that you have a conduction band electron and then you are adding over and above the donor state atom. So ND is basically the donor state atom and N0 is the initial conduction band edge. So if you want to find out the fraction of the number of donor states with respect to the total number of electrons, then we can write down that to be as ND upon ND plus N0, and that comes out to be this quantity here, right. ND we just now found out to be this much, 2 ND upon exponential minus ED minus EF. Similarly ND will be 2 ND exponential and N0 will be given by this quantity here, right. And this is a very straightforward sort of expression in front of you. And if you look very carefully, in this case the Fermi level will cancel out from this and this, and what you are left with finally ND upon ND plus N0 equals to this. EC minus ED is basically the difference between the conduction band edge and the donor species. So my conduction band edge is fixed and my donor level ED will start moving up or down depending upon the number of donor atoms available, right. Now EC minus ED is referred to as the ionization energy of the dopant species. Why? Because this is the minimum amount of energy which I have to give from an external source to semiconductor, so that electrons from the donor species is able to migrate to the conduction band. So if this is your conduction band edge and this is your valence band edge, and if this is your value of ED here, then I have to give an energy equal to this much for electrons to actually migrate to a higher energy level from here to here, right, migrate here, and you get ND upon ND plus N0, right. Now if I say that EC minus ED is exactly equals to 0, which means that ED is overlapping with respect to EC. So it becomes 0. So I get e to the power minus 0, right. So I get 1 upon e to the power 0. That means I basically get e to the power 0 equals to 1. I get 1 here. I get 1 over 1 plus NC by 2 ND. right. If I remove this, I get 2 Nd by Nc as the value at T equals to, at Ec equals to Ed. That is the Nd upon Nd plus N0, right, and that is standard way of looking at it. Now let us look at a numerical problem and see how the fraction is. What we are looking is, we determine the fraction of the total electrons in the donor state at T equals to 300 Kelvin. So you need to find out the reverse, you need to find out how many of the total electrons are available in the donor state, right, rather than which have actually moved to the conduction band edge. So if you solve it with Nd equals to 10 to the power 16 per centimeter cube, I get this value to be equals to approximately 0.41%, which means that 91.6%, 99.6% of the total donor species has actually shifted to the conduction band at 300 Kelvin, right. Now the idea is, if you would have gone this T to very low value, say around some, so I will give an example. Let us say that T tends to go to 0, absolute 0, or very low value. Then what I will get here is exponential. Let us assume this to be as equals to minus x, right, where x has got an inverse function on temperature. So if the temperature goes excessively down, so this is basically 1 by e to the power x, that is easier to understand. Let us suppose Ec minus Ed by kT. So as the temperature excessively goes down, this factor excessively goes up, which means that this factor excessively goes up, right. As this factor excessively goes to a very high value, then it effectively means that this quantity goes down drastically, right, and therefore this expression goes up drastically. Now if you look Nd upon Nd plus N naught, right. So if you divide by Nd, I get 1 upon 1 plus N naught by Nd, clear. Now if you would have given a very low temperature, let us suppose it's let us say T equals to absolute 0, then this, if this is absolute 0 here, if you place it here, this quantity becomes negatively infinitely low. So it's e to the power minus infinity, or I get 1 upon e to the power plus infinity. So this quantity shoots, it actually goes down drastically. It goes down drastically implies that this whole quantity denominator goes down, and therefore this quantity shoots up, which means that 1 upon 1 plus N naught by Nd shoots up, which shoots up primarily, meaning that your dopant species are almost giving you none, right, because it can only shoot up when Nd becomes larger and larger, right, and N naught should go to almost to a very low value, and that is the reason you will see that the concentration will fall down drastically at higher temperature. This is again a formulation where you calculate the thermal equilibrium concentration of electrons and holes for a given Fermi level. We are given that the conduction band number of states, and you are told to find the value of N0. We are assuming that the Fermi level is 0.25 electron volts below the conduction band edge. So I have a conduction band edge and it is less about 0.25 electron volt, right, and I am assuming the band gap to be 1.12 electron volts. So from here I can get that N0, which is given by this big function here, to be approximately equals to 1.8 into 10 to the power 15 per centimeter cube, right. It is way above the intrinsic value of 10 to the power 10, right. So simply looking at the difference in the conduction and Fermi level, you can predict the value of N0. Similarly, you can get the value of P0 as 2.7 into 10 to the power 4 per centimeters cube. This takes care of all the discussion on freeze out and incomplete ionization, and I wanted to tell you by this definition and by this discussion is one takeaway, just one takeaway, that carrier concentration is surely a function of temperature. Two ways we can understand: as the carrier temperature goes down, there is not enough energy for the electrons to get promoted to conduction band, and therefore there are no free charge carriers available to a larger extent. And the second way of looking at it, the Fermi level itself will be a function of temperature, and therefore the difference between the conduction band edge and the Fermi level will give you the amount of free electrons available. This is another numerical problem and almost the same as the previous one. What we are showing is they calculate the probability that a quantum state, or forget about quantum state, you must have not learned it, that there is a state in the conduction band, and where is it? It is Ec plus kT by q, which means that the state is at energy kT by 2 more than the conduction band edge. The question is calculate the probability of occupancy at T equals to 300 Kelvin. Fermi level is 0.25, the value of Nc is given as this much, right. So, if you look at the Fermi level, we know that Fermi level is 1 upon 1 plus exponential E minus EF by kT. If you take it to the top, do a small manipulation, I get E minus EF. What is E now? The new value of E is nothing but EC plus kT by 2 minus EF by kT, right. And from here what I get is Fe to be equals to, if you place the values, I get this much the probability, which is very very low, and the electron concentration, if you find out, comes out to be equals to this much value, right, which is this much, which means that the probability of finding the electron is very very low. It is just 3.9 in 10 to the power minus 5 is the rare electron, which means that most of the charged particles or most of the electrons will be occupying the lower energy states, which is the near the conduction band edge. So, this takes care of our understanding of variation of temperature and its effect on the carrier concentration. What we will do now is, now we will start looking at the temperature dependence of band gap energy, carrier mobility, low temperature thermal conductivity. Let us look at the temperature dependence on band gap energy. So, there is a model known as Varshini model. This is a model where band gap energy is directly a function of temperature, and it is given by this formula here. It is an empirical or semi empirical formula derived from experimental as far as a numerical value, and this is given as EGT. This is the band gap with respect to temperature here. This is band gap at T equals to 0 Kelvin and minus alpha into T square upon T plus beta. T and alpha and beta are the variations. Now, if you place and do this Varshini model on the scale, then on the x axis you have this band gap Eg and the temperature. So, at T equals to 0, it is the highest, let us suppose 1.17, but as you make the temperature go higher and higher, the band gap starts to fall, and at 300 Kelvin it is 1.12, right. You might be asking, it is not a big change, right, it 1.17 to 1.12. However, please understand that this small change, which apparently a small change, actually changes the carrier concentration drastically, and that makes the temperature dependence on band gap pretty important sort of parameter to check in the sense. This is of course an experimental data, and the beta value is 655 and alpha value is 4.9 into 10 to the power minus 4. Since there is a T square dependency, you see it is not a linear profile which you see here. It is almost like a reverse parabolic profile which you see. But let us see, why does the temperature change like this? Why does it happen like this, right? With increasing temperature, why does the band gap actually reduce, starts to reduce? This is to do with more of the m star value, which means basically the effective mass value of the electron. They changes with respect to temperature, which results the shifting of the valence band and the conduction band with respect to temperature. The conduction band starts to shift down and the valence band starts to shift at the top. The difference therefore starts to become lower and lower at larger temperature. Now, let us come to the mobility, because mobility is an important term in terms of temperature. So, there are two aspects of it which you should be aware of. At lower temperatures, right, impurity scattering dominates, and it is T to the power 3 by 2, a positive 3 by 2, which means that as the temperature increases, the mobility starts to become larger and larger. So, that is the reason you see here impurity dominates, and at higher temperature lattice scattering starts to dominate. Impurity is the impurity atoms which you have given by virtue of doping, and lattice scattering is not only the dopant species, the silicon species which are sitting at their fixed places, they tend to scatter the electron, and therefore mobility starts to fall down. Why does the mobility actually changes in the manner which you see here is, therefore there is something known as a sweet spot at certain temperature where you will find that the mobility is actually the maximum one, right, and mobility is lower when you go a temperature at a lower value and then goes again low at higher value, right. So, this scattering phenomena is primarily the reason why you get variations in the mobility with respect to temperature. Now, there are two types of mobility scatterings are available, and the way we calculate the total mobility is what is known as the Matheson's rules, right. So, there is a known as a Matheson's rule, and it adds the total mobility, the effective mobility is equals to 1 by mu I plus 1 by mu L, where mu I is the mobility due to ionized impurity scattering process and mu L is the lattice scattering process, and mu is the overall mobility which you see. Now, if these two are independent scattering mechanisms, and therefore their inverse mobility are added, right, and therefore the net mobility actually is lower than the least. It is almost like remember resistance is added in parallel, The concept there was obviously it will be less than the least. Similarly, when you add mobility, the overall mobility will be always less than the least mobility, right, and it is a function of the impurity scattering mobility, and it is also a function of the lattice scattering mobility in both the cases. This is actually from one of the papers we have taken this data, and this shows how does the mobility varies with respect to temperature, and what is the generic sort of expression to take care of the mobility versus temperature variation. So, on the left hand side, if you see the graph here, it plots mu naught, which is the low field mobility, with respect to temperature varying from 4.2 Kelvin, and there were 3 plots at 77 Kelvin. So, this is your liquid helium, this is liquid helium, this is liquid nitrogen, and this is room temperature. So, there are 3 temperatures which are available, 4.2 or 4.4, which is around liquid helium. We have 77 K, which is liquid nitrogen, and we have room temperature 300 Kelvin, which is there. And what the author has plotted is, they have plotted the variation of the mobility with respect to temperature right from 4.2 to 300 for various types of devices and various aspect ratio of devices. Say for example, the first one is 3 micron by 1 micron NMOS device, right, which you do, and then you have a 3 micron by 1 micron PMOS device, right. You can compare this with this. You see the overall mobility for a PMOS device is lower, expected also because hole mobility is lower than that of electron mobility. Interestingly, however, the mobility actually starts to go down as you make the temperature go higher and higher. So, at lower temperature, the mobility actually shoots up, and the reason is that you have less amount of scattering available with you. That is very important term which you should be very careful about, and maybe one of the major areas in which people are looking currently into. Similarly, if you look at 3 micron by 28 nanometer device, the last one, now quite interestingly you see what is happening, and maybe you can think about it. For an NMOS, which is W by L is 3 micron by 28 nano, you see this reversal has happened. NMOS has got a lower mobility as compared to PMOS. NMOS has got a higher mobility 300 nanometer with respect to 28 nanometer W by L, and if you take a 3 micron, and so this is 0.3 micron. So, higher the width of the device, lower is the mobility. So, 2 things you need to worry about is W by L ratios and temperature. If the W by L ratios are exactly the same, obviously PMOS will have a lower mobility as compared to NMOS, and if the device is same, higher the width of the device, lower will be the mobility available to you. So, what they did was that they used this and used a fitting parameter to find the generic solution of mobility with respect to temperature, and they found out mu to be equals to mu naught low field mobility at 1 plus theta times gate bias minus threshold voltage of the device, right, where mu naught is defined as the low field mobility, theta is defined as the mobility reduction factor, and Vt is the threshold voltage which you get. So, Vg minus Vt as it goes on increasing, mobility drops down, right, and the expected also. So, when the gate voltage becomes closer and closer to threshold voltage, more scattering happens because now the charge carriers are closest to the silicon dioxide interface, right, and since it is closer to the silicon dioxide interface, the rate of scattering will increase, and as a result the carrier mobility will decrease. Therefore, since we have studied now the mobility and the carrier concentration, we will now look into the electrical resistance of silicon block, right. And so, we are on the y axis we are plotting resistance in ohms, and on the x axis temperature of a simple silicon cross, and for various values of the doping concentration starting from 10 to the power 14 to 10 to the power 18 per centimeter cube, right. Now, interestingly, when you make your dopant species very high, your resistance it drops down, expected also, because now you have a larger dopant species means you have a larger number of free electrons available. So, therefore, the resistance will drop down, and that is true also. You see, this is the lowest value of resistance which you get, which is the highest value of doping concentration. But interestingly, with temperature it does not vary. As you lower the doping concentration at Nd equals to 10 to the power 14, you see it actually reduces 10 to the power 8, right, and it goes suddenly down and remains constant almost. Why is it increasing is primarily because at such a low value of Nd, your carrier freeze out has happened, you do not have large number of carriers available, and therefore the resistance becomes high. But just as you increase the temperature slightly around 77 K or 80 K, the resistance sharply falls down because suddenly you have large number of electrons available which can participate in the current flow. and that is the reason this is how resistance versus temperature graph typically looks like. Now let us look at the thermal properties of material at high temperature. Obviously, as you make your temperature larger and larger, there will be increase in the phonon activity and there will be thermal expansion available. Moreover, there will be heavy phonon scattering. As a result, there will be a reduced thermal conductivity. This is thermal conductivity, this is not electrical conductivity, this is thermal conductivity. So as you can understand, why is it like that? As the temperature becomes higher and higher, the lattice which was sitting quietly, the lattice was sitting quietly here, right? The lattice was sitting quietly here. Now as you increase the temperature, its vibration will take place in both sides, effective vibration. As a result, the probability of scattering will increase, and therefore you will have more thermal expansion, more phonon activity scattering, and there will be a reduced thermal conductivity of the system, right. And this is the major phenomena which happens at high temperature, at very high temperature. Now if we look at the thermal conductivity versus temperature, then this is how it looks like. Thermal conductivity primarily means that for every 1 watt of power which you give, if I want to check how much amount of temperature rise is there per centimeter, is defined in thermal conductivity, which means that higher the thermal conductivity, more rise in temperature means it is able to conduct the thermal energy very fast from point A to point B for that particular material, right. And it comes from at low temperature, thermal conductivity is very low, right. You do not have to go into the detailed physics of it, just understand for this will be important for the subsequent lectures, that at very low temperature, somewhere here you see your thermal conductivity is very low. Similarly, when you go to a very excessively large temperature, your thermal conductivity also goes very low. Somewhere around the middle, around this part, which is around 20-25 Kelvin, you will see that the thermal conductivity is at its maximum value. I am not going into details of all these things at this stage, but have a look at this source paper to get more information if you are interested. But since this is intended for higher UG and a lower PG level students, if you are interested, please go through this source. But I need to show you one important point here, that there is a sweet spot somewhere around 25 to 20 Kelvin where the thermal conductivity is its maximum, and then it starts to lower as you move below, and you move above that temperature, right. There are multiple reasons for such a phenomenon. On the left hand side, there is thermal conductivity for various elements. If you see, all the elements follows this hump curve which I showed to you in the previous slide. All the elements, they generally follow this hump curve, and as you can see from all these elements, you can see that this is for gallium arsenide, for diamond, copper, silicon. So this is for gas, gallium arsenide. This is for diamond, copper, silicon. If you see for silicon, it is exactly the same as we required. If you look at gallium arsenide, it is something like this, right. It is having the same maximum thermal conductivity, but at lower temperature it is at a higher thermal conductivity as compared to silicon, and at higher temperature there is a lower conductivity of gallium arsenide with respect to silicon. When I say thermal conductivity, I have already discussed with you the expression and the phenomena, why is it like that. But most of them, all the material typically follows a hump curve. So all of them follow such hump curve here, right. It is lower, so please understand, it is lower at very low temperature, lower at again very high temperature. Somewhere in the middle, it has got the maximum temperature available to us. Why do you want to study thermal conductivity? See, typically at low temperature, right, you need to maintain temperature of around 4 Kelvin or 4.2 Kelvin or 4.4 Kelvin, where your electronics are, right, and your qubits are placed at millikelvin. So around 1000, so around 3 orders difference of temperature is there. Let's concentrate on the electronics part here. You will have too much amount of self-heating in devices. Self-heating means the current will increase, the current I square into R will increase, that will increase the heat. When the heat increases, electron hole pair generation takes place, more current is there, and this will happen. So we should find a methodology by which I can relate the material of the electronics to the thermal conductivity, and therefore we should know how fast the heat distribution can happen in a devices. And therefore we should know how a thermal propagation takes place. That means how does the electronics will propagate its thermal properties outside the hotspots, right. And then optimization for cryocemos efficiency, what does it mean is, how do we therefore optimize? We will take up all these things later on, but I want to just put into your mind these basic 5 questions to you. First is the self heating, second is thermal propagation, the third one is the impact of low temperature operation. So when you are working at effectively at almost freeze out conditions where your devices don't have too much amount of thermal conductivity, how does it impact the overall device characteristics? And then, though the fourth point, analytical modeling of thermal management, is required, but it's not a very important one at this stage. But more important point is the fifth one, where we need to optimize the cryo-CMOS efficiency, right? So let me recapitulate what we learned in this lecture, and we learned about 2 important points. We learned about thermal conductivity, this major new term which we learned, thermal conductivity. We also learned about material dependence of thermal conductivity dependence. Then third point we learned about was the freeze out concept and how is it temperature dependent, right? And then finally we learned the last one which we learned was the motivation for going ahead in this domain. So these are the 4 things which majorly learned, and we try to keep it very basic one, though there are large number of research papers available. Those who are interested can contact me over email and I can send them the research papers. However, for moving ahead, this much amount of information will be enough at this stage. As we move ahead and dive deeper into other subjects or other domain, I will start giving you inputs about that as well. With this, let me thank you for your patient hearing. I will meet next time.